Begin immediately. My task is to talk a little bit about the climate change, the realities, the risks, what has been reported, and what is probably true, and what is certainly not true. So let me begin by, let's see if I go up. So many people have said that the climate and the amount of CO2 has changed many times in the past when there were no humans. And so why should I believe this change is any different? And I have to first say that the fact is they are right that the climate of the Earth has been changing for its entire history. And this is one example of the lower panel in blue is the climate record history for the last 800,000 years. Temperature change as gleaned from ice core data, and we also have in green and in orange the carbon dioxide and methane concentrations. And so I note, for example, that Neanderthals roamed the Earth around this time, that Homo sapiens roamed the Earth about this time, and for most of this period of time, virtually all of it, it's safe to say that these people and human people, Neanderthals, had nothing to do with climate change. So I also note that very, very recently, in the last 50, 80 years, the levels of carbon dioxide and methane have increased dramatically compared to changes on a geological timescale. Furthermore, if you go back even further in history, in the climate history of the Earth, you find that in the extreme left-hand corner, bottom corner, that those ice ages, between ice ages and quote warm periods, are those oscillations that you see on the extreme left-hand side, 800,000 years. The scale of this is 60 million years. And what you see is that for most of the history of the Earth, going back 60 million years, the Earth was much, much warmer than it was in the last 800,000 years, even in the warm periods of the last 800,000 years. And so the natural climate of the Earth is actually considerably warmer than it is today. There's a complicated set of reasons why. I don't want to go into it, but just say that there's no exquisite thermostat maintaining the temperature of the Earth at work. This is more recent data on carbon dioxide over the last roughly 10,000 years, and you see that it varies slowly over this time scale until you get about to 1900. And then something essentially happens very quickly. And so I should say that this rise over the last 10,000 years, 3/4 of the increase happens to be over the last 65 years, and the current level is up here. Right? So this is not a geological time scale. Indeed, let me go back one. Indeed, the amount of CO2 that we've seen come up in the last 100 years is quantitatively consistent with bookkeeping. Bookkeeping in the sense that how much CO2 have humans emitted, and 55% of that is immediately absorbed by the oceans and land, and so what is left is what you see. That increase is consistent with our understanding of what we emitted and how the Earth responds. All right? There's a claim. There were many warming periods in Earth's history, and recent unprecedented, this is quoting out of a blog, a posting in the internet, the recent unprecedented warming is naturally occurring change as we come out of many ice ages. And so this is something you can actually find on the web, and it shows ice core data, and it shows a period of time, and you see you have Bronze Ages, Roman Iron Ages, medieval warming on the higher side, you have Dark Age cooling, you have Bronze Age cooling, and over the last 1,000 years, we were in what we call a little ice age. And the point of this article is to say the data itself shows that we're just returning back to the norm. This is all there is. And so the question is, what is going on? Is this real data? The answer is, it is, but it's only partial data. If you look at all the data from all the ice cores including the present time, what you find is something very different. We're here in our present global temperature, and then from this you can say, no, we've done better than climb out of the little ice age, which we have done. We've gone well beyond the little ice age, and we've gone above what happened over the last 1,000 years. So the fiction is a partial truth. And when new data comes that disagrees with them, they don't update the website. They just keep on posting the partial truth. And this is a favorite tactic. All right, so there's fiction that said from 1998 to 2012, the global surface temperature has not been increasing. And since climate models did predict the global surface temperature was increasing, they were wrong. And if they're wrong in the past in predictions, how can we ever trust them in the future? So this is the data that they were talking about. And you see in those little dots on the right-hand corner, now there's a high point in 1998, then it dips down for 2 years, and it comes back up. And for the period of time between 2002 to 2012, there was a plateau. And so what is going on here? Well, again, data was not updated. Number one, that red arrow, they don't use that red line. The red line is a moving average, and they were just selecting the data that showed a plateau. And there was a plateau if you just select that data, and that's the plateau. However, that's the full record. Okay, and so it is absolutely true that the climate scientists did not predict this mini plateau, which you can see in the time average red line. And so what is going on? Why were the climate models wrong? The climate models were not wrong if you average over about 20 years, but they were wrong if you average over a decade, and tried to pick the decade where they were most wrong. And so this brings me back to something I experienced when I was Secretary of Energy. In the summer of 2010, I spent 2.5 months, half-time there, helping BP put out their oil leak. At the surface of the Gulf of Mexico during that summer, the temperature was quite hot. It was 30 degrees centigrade. It was like a warm bathtub. Down 1 mile deep, where the oil was leaking out, the temperature was 4 degrees centigrade, and it does not change by a fraction of a degree, summer or winter. The point here is that warming, the top can go up and down a lot, but 1 mile deep, the ocean temperature is quite constant and very cold. And so what we know is that it takes a long time to warm up the bottoms of the oceans. How long, we don't know exactly. It could be 100 years, it could be 200 years, it could be 300 years. So the equilibrium of what we've done today is not known. So let me continue the story. So over the last decade, we have been dropping these floats. These are called Argo floats. Those are those little yellow things. We don't drop the people. From airplanes. They are battery powered. They sample the surface temperature of the ocean. They go up and down, sampling anywhere from the surface temperature down to 2 kilometers deep and come back up. Every 10 days, they radio their signals back of what they've done. And they're just floating around the ocean. Now you might think, well, what is this going to tell us about the ocean? Because, you have a couple of these buoys bouncing around, and what we really want is, globally, what is the ocean doing? And of course, scientists realize that, so they put this number of buoys around the world. Roughly 4,000 of them have been bobbling around, radioing data back. And the amazing thing is, what they found is energy is conserved. What does that mean? We use satellite to measure how much radiation from not only the visible light, but from the infrared light, from radio waves, from sunspots, ions, everything hitting the Earth. We also use satellite to measure how much heat is being given off by the Earth. We can measure cloud cover, we can measure all these things. And so then you say, energy in has an 11-year cycle, we measure it, it's not theory, it's a measurement. Energy out, less. Where's the energy going? That was the issue that scientists were thinking about. The climate skeptics were saying, oh, you guys don't know anything about what you're talking about. And what this data showed us is that the deep ocean mixing changed a little bit faster than we thought, and the heat went into the ocean. Quantitative agreement. Energy is conserved. Okay? The debate among scientists was not what the climate skeptics were saying. All right. Are glaciers melting? Is the sea level rising? People go around and they take pictures of glaciers. Historical pictures, August 1941, Muir Glacier. August 2004 looks kind of different. So they say, aha, the climate is changing. The skeptics say, this is anecdotal evidence. That's with just one glacier. I happen to know of other glaciers that are shrinking. So in order to know what's really happening, shouldn't you be looking at all the glaciers and be taking photographs? All right? We do that. We do it by satellite. We have 2 satellites that orbit the Earth, and as ice cover changes, as water aquifers under the ground change, it disturbs gravity. And when it disturbs gravity, it disturbs these orbits. And when it disturbs the orbits, it allows scientists to back calculate what's the change in local gravity. It's more subtle than that because, well, I guess I'm not sure why it's, never mind. It's more subtle than that because as the ice melts, the land rebounds. It's elastic. And so you also have to measure changes in the land. Anyway, when you do all of that stuff, what you find, much to our surprise, is that Antarctica, which was earlier predicted in year 2000 and before, Antarctica was predicted to gain in ice mass. How does that make sense? Since the Earth is warming. The Earth is warming, more evaporation, more rain, more snow. Antarctica is so cold that the snow accumulation will be faster. And so Antarctica was expected to gain in ice mass. What we found, much to our surprise, is it is losing in ice mass, and losing very rapidly. There are little pockets where there are gains, but on balance, if you look at the whole continent, there has been a steady loss in ice mass. As I said, not only much faster than predicted, we got the sign wrong. It was much worse than we thought. Let me also point out, you saw in one of the earlier slides, the temperature in that last warm period was only 1 degree warmer than we are today. But we know as historical record, again, not climate models, but history, that the sea level during that period of time was 6 to 9 meters higher than today. How do we know that? Because there are critters that live on the borderline between land and ocean, the sea ocean. We can radioactively date them. We find out when they're fossilized and where were they living. You go all around the world and you find, lo and behold, the sea level was much higher. Those fossilized creatures are 6 to 9 meters higher. Okay? These fossilized critters and those things were 6 to 9 meters higher. Very scary concept. But what does this have to do with the present day? The present day, we used to think it would take a couple of thousand years to get 6 or 9 meters higher. Now with these new measurements, we're thinking, okay, in this century, it's still only going to be a meter. That's the lower panel. And the range of predictions depending also on our emissions. It's not much. It's about a meter, maybe a little more, maybe a little less. But that's not the scary thing. In the next century, from 2100 to 2200, you're up to 5 meters, and 1 century after that, you're up to 10 meters. Okay, so this is Shanghai, Pudong area. It's not going to look very good. It'll look very different when the sea level is 10 meters higher. Shanghai is a big city, and so this is Shanghai, the greater metropolitan area of Shanghai. In the upper left-hand corner, you can see the city, used to be village. My father was born in Taichung, and this is what it looks like today. If we achieve the UN goal of 1 degree warmer than today, this is what Shanghai looks like. Most of Shanghai is underwater. But it's no longer going to be underwater 2,000 years from today. It'll be underwater 200 years from today, 150 years from today. So this is a very different concept. It goes from evolution to an adaptation to evacuation. So that is coming along. Houston had many rainfalls. In 2015 and 2016, there was 2 once-in-a-500-year floods in Houston. In 2017, because of Hurricane Harvey, it's been labeled a 1-in-1,000-year rainfall event. And as a scientist, I say, we don't have 100 years worth of rainfall data in Houston. We probably don't even have 60 years, but let's say 100 years. How can people be claiming this was a 1,000-year event? What is going on? And in actual fact, I think some of the claims that I see bandied about by weather people are a little bit funny. Okay, these are 7 years of 500-year storms in the United States. So if you look past the last 500 years in the U.S., you see these storms. Okay, again, we don't have the rain records, so what is going on? And let me show you this movie of the temperature of the Earth from 1961 to 2016. A redder gets hotter and hotter and hotter. This is not a good story. Okay, but you notice something. Most of the increase in temperature is in the northern regions, in Alaska, in Siberia, Russia, and northern Canada. And so what most people really want to know is how is it going to affect me, where I live, in the United States, in China, in wherever, sub-Saharan Africa, in Australia. And so, to that end, we really want to know we're not as interested in what is happening on the average globe, we're interested in the countries we live in, and policymakers are interested in what happens in the country they live in. And so I'm going to go very quickly through this. I just want to say that I and a few other people have gotten hold of a climate scientist, Kevin Trenthoff, but this is mostly a mathematics statistics paper trying to analyze trends of extreme events. What is that? What the question we ask is, the 1-in-100-year rainfalls, are they actually increasing? And can you actually tell from data that does not extend 100 years? And the answer is, if you have a very, very dense data set, and in this data set we have 1.5 million data entries per day over a 38-year period over the entire United States. No other country has this. And so we tried to do Europe, but we couldn't. And then we use satellite data to interpolate between the ground measurements. For example, if you're in a very desolate desert, you don't have a lot of rain gauges in this big desert. But the satellites can tell you, over reasonable regions where it was raining, where it was not. All right, I'm going to skip this and get to the bottom line in temperature. If you define 1-in-100-year event to be an event on average occurring once in 100 years in this 38-year period, what we found is that at the beginning of this time, it was occurring at lower probability, and at the end of the time, it's occurring at higher probability. And the 1-in-100-year events are now occurring once every 33 years. This is purely statistics, no climate model. But it's the tip of the iceberg, number one, and number two, mostly increases in the last 2 decades. Okay, very, very disturbing. But also, we now have a statistical tool where countries going forward today, putting out rain gauges and temperature, and then using satellite, which everybody will has access to their own satellites, can do this dense interpolation. So in the next 20, 30, 40 years, you can see where these extreme events, are they really increasing? With the question people really care about in my country, not in northern Alaska. All right, there's a claim, there's no proof that the increase in CO2 is due to human activity. In fact, that is not true, that is false. And there is smoking gun evidence that the CO2 we see is not due to natural carbon cycles. So let me explain this. If you look in the upper atmosphere, we're being bombarded by cosmic rays, protons mostly. The protons hit the nitrogen in the upper atmosphere and it turns it into a radioactive form of carbon called carbon-14. Now carbon-14 then drifts in the atmosphere, drifts down, mixes with the biosphere, and all living things incorporate carbon-14 in themselves. You and I have carbon-14 in ourselves. There's some certain fraction, depending on how much is made in the upper atmosphere, how long it takes to drift down, and all this other stuff. Carbon-14 has a decay time of 5,700 years. Now suppose you die, and they put you in a really good coffin, deep underground, and you're no longer mixing with the biosphere. Within 3 or 4 lifetimes, say 20,000 years, all the carbon-14 in you has decayed away. It's gone. Now they take you out, they put you in a power plant, you and all your friends, and they burn you for electricity. And if there's enough of you, there's more carbon that's emitted, but that carbon doesn't have carbon-14. It's been isolated from the Earth. And if there's so much carbon that's been isolated from the Earth for a long period of time, and significant enough, you actually dilute the amount of carbon-14 to carbon-12. So here you have a curve which says this increase in CO2, and the green curve is the decrease in carbon-14. Now, the data runs out in 1950, so I'll show you the more recent data. And here's the more recent data from 1950 to the present time, nearly the present time. And you see around 1960, the carbon-14, both northern and southern hemisphere, the green and the blue are northern and southern hemisphere, shoots up like crazy. Okay, what's going on? H-bomb testing. Atmospheric H-bomb testing by Russia, Soviet Union, and the United States makes lots of carbon-14. The carbon-14 then mixes with the oceans, so it's a beautiful, you see this delay, the oceans are picking up carbon-14, and it all continues, and you get that to the year 1990, 2000, and it looks like it's now declining. There's an equilibrium between the carbon-14 in the atmosphere and the oceans, great stuff. What's going on? What about the decrease in carbon? Guess what? It agrees quantitatively with the burning of fossil fuel. The dilution of carbon-14 that we now see after coming to this equilibrium after H-bomb testing is in quantitative agreement with the amount of fossil fuel we're burning. So this, most scientists regard as the smoking gun. This, you can't blame it on trees and critters in the ocean. They don't cycle over 5,000 years, okay? Claim, oil production will soon peak, and then the production will decline and prices will increase as supplies run out in the coming decades. So the problem could take care of itself. We run out of oil and gas. Now I want to quote some people I deeply respect, and they wrote, "Our ability to find and extract fossil fuels continues to improve. Economically recoverable reservoirs around the world are likely to keep pace with rising demand for decades." Okay, I said that, someone I deeply respect, in 1912. And so we published this article in Nature, as a 6-page review article about what's happening in energy in nature, and it's come to pass. Let me, oh how sad. Somehow the slide did not appear for the oil production in the United States. It peaked in 1970, went down, 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 and because of new oil technologies, and especially hydraulic fracturing and horizontal drilling, the oil production in the United States actually went higher than the old peak of 1970, and then it went down because we're so awash in oil. We have so much oil around the world that the prices have collapsed, and we went from $100 a barrel to about $40, $45 a barrel. And so production declined because the price collapsed, and the reservoirs of oil in the world are at an all-time high. And most of the oil companies I know are gearing up to think that for the next at least couple of decades, at least for one decade, the price of oil will remain around $45 or $50 a barrel, because the ability to find new reserves of oil, to get out more oil out of the old reserves, has pushed ahead. The technology has improved. All right. Oh, here's the curve. Sorry, I just messed up the order. Okay, so let me go backward and just say that this black line is our cumulative carbon emissions, that 2,900 gigatons of CO2 is the UN danger point if we exceed that line. there's at least a 1/3 chance that we will go above 2 degrees centigrade since the beginning of the Industrial Revolution, a little bit less than 1 degree today. Again, that goal is to keep the sea levels to 6 to 9 meters. Okay? What's the probability that we will go over that line? I'm a betting person. I'll give you 100 to 1 odds we go over. Right? It's not certainty. Scientists don't have certainty, but I'll give you 100 to 1 odds. 3/4 of the greenhouse gas emissions occurred in the last 65 years. Very, very scary. All right, so let's continue on this. Let's talk about potential solutions. And there's a claim that society cannot reduce CO2 and other greenhouse gases without damaging the economy significantly. Let's examine how true that is. I'm going to skip this, and I'll talk with things that may or may not damage the economy. We have in the United States, and also in China has it, appliance efficiency standards, and they are designed to save energy, but the people who oppose efficiency standards say that forces people to purchase more expensive refrigerators or air conditioners or something like that, so they're less affordable. So people are being denied the chance to own refrigerators or air conditioners. And that is the claim, and in the current administration, there's a concerted effort to decrease and get rid of many of these standards, okay? Because they're looking out after the American public. All right, let's examine the facts. Here are the facts. If you look at refrigerators, for example, this is a paper I published with some colleagues in 2014. The red line are the purchase price of refrigerators, where you adjust for inflation based on consumer price index. And those arrows were appliance standards starting in California and going to national standards. The blue lines are the cost of both purchasing the refrigerator and over the 20-year lifetime of the refrigerator, what's its energy cost. And what you see as you go and put in more and more refrigerators, this is a logarithmic curve on the x-axis, the cost declines. Surprisingly, in refrigerators, the expectation that the purchase price of refrigerators would go up did not come true. And we thought, well, that was interesting. So we looked at clothes washers, we looked at room air conditioners, we looked at central air conditioning, and it was highly correlated. As soon as you put in appliance standards, the purchase price went down. We were very excited by this data finding. We submitted the paper to Science magazine. It went out for review. It went to 3 economists. It came back and one person said, "This is astounding, this is big news." The other 2 economists said, "I don't care what these people say, the economists are not going to believe it." Okay, so when you have data that doesn't agree with your world view, you're just not going to believe it. And then I said, at least a certain class of economists aren't really scientists. Okay, so indeed, let me just say, you can ask the question, how many free market economists does it take to change the light bulb? Why am I talking about the free market? There was the presumption, the religious edict that said, under no circumstances, if you could make a cheaper refrigerator for less money that was more energy efficient, you wouldn't do that. It's just impossible. So they couldn't believe it. And so how many free market economists does it take to change the light bulb? The answer is none. If the light bulb needed changing, the free market would have done it. And that was the religious conflict with data. All right, let's move on. The claim, coal is abundant, it's much less costly than wind, solar, nuclear, natural gas. And if you're in a developing country, your first priority should be to continue to grow your GDP. The United States did this, Northern Europe did this, we should be allowed to do this, so we're going to do it this way. So let's examine this. For example, the price of solar around the world from 2013 to 2016, now 2017, has dropped to 1/3 of its price. Only 4 years ago, it's dropped to 1/3 of its price. And now there are contracts. These are unsubsidized prices, contracting you buy 2.5 cents a kilowatt hour, full cost. You know, you build this thing here, you pay us rent, you do this, and we'll buy electricity from you at this price. Just in case you probably don't know what the cost of electricity. How many people here in China know what they're paying for electricity? Nobody. It's interesting. I think it's about 10 cents, 12 cents a kilowatt hour. It costs about 6 to 8 cents a kilowatt hour for wholesale electricity. Okay? This is, you can't read the thing, so I've just boxed in red. I didn't have time to make the contrast higher. But this is an analysis in 2016 of cost of, the upper box is the cost of unsubsidized solar, the cost of unsubsidized wind, and the cost of natural gas, assuming some low-end cost for natural gas for the next 50 years of the plant, you know, which would be historically low, not as low as today, but much lower than it was in the last 20 years. And what you're seeing is wind and solar in the United States, unsubsidized, is now comparable to natural gas. The energy cost in the United States is about 1/2 of what it is in China. Okay? So these are unsubsidized costs. Now, this is a prediction, so it's not a matter of fact or fiction because it's just a prediction. Already in many places in the United States and around the world, we have already achieved 3 cents a kilowatt hour, but I think in more places by 2020. And costs will continue to decline to maybe 2 cents a kilowatt hour by 2030. I'm on a council that advises Shell and the CEO of Shell, Royal Dutch Shell. Shell thinks that by 2040, the price of renewable electricity will be 1.5 cents a kilowatt hour. That's an oil company. Okay? Claim we have all the technology needed to transition to 100% renewable energy. All we need is the political will. Many of my colleagues at Stanford say that. And here's the fact, that the full cost of renewable energy is not just the wind or solar. Once you get to 20, 50, 70% renewable energy that's intermittent, you need backup generation, energy storage, enhanced transmission, distribution. Those are costly things. And so that really is in the full cost. So as the price of solar and wind come down, they continue to come down, and you're going to outpace with coal and natural gas. You actually need it that way in order to actually maintain parity with those fossil fuel sources. Now, it's a fact that there is no economically viable technology for long-term, and by long-term I mean seasonal storage. Here's what we consume in terms of the number of kilowatt hours of electricity per year. It's 10 to the 13. 10 to the 9 is a billion, 10 to the 12 is a trillion, 10 to the 13 is 10 trillion kilowatt hours of electricity. If I take the cost of battery storage for 2 months to be half of what it is today, I find that we need $1,000 trillion to store 2 months of energy. So this is why I mean by not economically viable today. All right? We don't have that. And so the challenge of the 21st century is actually to develop liquid hydrocarbons from splitting water into hydrogen and oxygen, or reducing carbon dioxide into hydrogen and carbon monoxide. And if we can do this with this really cheap 2 cents a kilowatt hour electricity, then we have a liquid battery. The liquid battery is a big deal. So, because this means that we can capture carbon dioxide. We recycle it. We don't capture and sequester it. We recycle it. We put it into a fuel, starting with methanol, but even higher hydrocarbons. Or you take water and split it and turn it into a fuel. And this energy can be put on a transcontinental transmission line. That's the transcontinental transmission line. It's called an oil tanker. And this oil tanker goes everywhere around the world, and it ships oil anywhere around the world. And what's the cost of shipping that oil? It's the equivalent of 2 cents a gallon for gasoline. The shipping and storage cost of oil actually add only 2 cents, 2 pennies per gallon of gasoline. So it's a very cheap transmission line, and it's a very cheap way of storing energy. And so it's this form of storing energy which will ultimately be our battery. And this will be the transcontinental or cross-ocean transmission lines we will need. And so let me just close by saying, reminding you of my favorite picture, one of my favorite pictures, Earthrise, taken Christmas Eve, 1968. I was in college. And this is the mission that orbited the moon in preparation for the lunar landing. And on the last orbit, they turned the capsule earthbound, and an astronaut, Bill Anders, took this picture. And after he took the picture, he said, let's see if I can go like that. We came all this way to explore the moon. And the most important thing is we discovered the Earth. When you step back and look at what's happening, you look at this lunar landscape, not a good place to live, no water, no air. You look at the Earth, very warm and inviting, and you see black all around you, nowhere else to go. Since 1968, the evidence that humans are changing the climate has become very compelling. Maybe in the 60s or 70s, not completely convincing to most scientists, but by 2016, any scientist who reads the literature and begins to study this is saying, it's fine-tuning our understanding. You know, what will be the consequences? Will they be bad, very bad, or catastrophic? It's not, well, it happened. It's not whether humans are causing it. It's none of this. And yet, in the U.S., at least 40% of the Americans don't think this is happening. So that's a fact. Thank you. Am I done? Should I move on? How long did it take?
Thank you.
Are there any questions, or are we out of time?
I think people in Florida, Texas, and I think it might be happening.
Oh, the comment was people in Florida and Texas may think it's happening. It's hard to say. If you talk to the mayor of Miami and you talk to some of the Congress people who represent their constituencies near the coast, Republican or Democrat, they say, of course it's happening. I don't know if the governor has changed his mind in the last 2 weeks, but a year ago he forbid to use the word climate change in the state government. He said it's nonsense and I don't want to even see that word. In Texas, the verdict's not in also. It is very ironic, but in the Midwest, farmers are very independent. And if you work on the land and you've been doing this for 30 or 40 years, you begin to notice the weather has been changing. The planting season's earlier, you know, the summers are hotter, there are more droughts, all this other weird stuff. But they don't acknowledge that we don't use the word climate change. But if you ask them, has the weather been changing over the last 30 or 40 years? Oh, of course. What about climate change? No, bad word. We don't use the word climate change. Fishermen in the East Coast, they have to steam further north because as water gets warmer, there's less oxygen, less nutrients, and so the fish go north. And so the fishermen in South Carolina have to spend lots of money in diesel fuel, lots of time going further north chasing the fish. It doesn't happen overnight that the fish are going north. They're just going to where there's food. Again, they don't want to talk about climate change because it's been politicized. But they see with their own eyes that something has been changing. Any other questions? All right. Yes?
How can we educate the public and get the opinions to shift?
Okay, the question was, how can we educate the public and get these people to shift? Is that right? It's difficult. It's difficult for two reasons. If you talk to them as though, well, they're very they're not knowledgeable, they're ignorant, and you begin to lecture them, it does not help. It just puts up their backs, and especially if you tell them that the position, I don't really care about climate change, that might happen 100 years or 200 years from today, and I care about myself. And if you respond, that's immoral, you've 100% lost them. And so what one needs to do, and I haven't figured this out, I've been doing this for 12 years, but I still haven't figured it out, is how you can show, number one, that the solutions are actually becoming the low-cost solutions, because there's a lot of misinformation, there's a lot of fiction out there that renewable energy will always be more expensive. Now, people from North Dakota, Iowa, Texas, all these strongly Republican states, they love wind. It's cheaper. It's cheaper than natural gas. It's just, they love it. They're making lots of money. And so, but it conflicts with the fact that there are fossil fuel companies that want to remain in business, and they're willing to pay campaign contribution donations. And the second golden rule in politics is to get reelected, and to that end you need campaign contributions. So that's another dynamic that's going on. But the serious question is education. Talk about opportunities, talk about it's not going to be that expensive, and it may even be the lowest cost solution. And once the technology is equal, and for example, electric vehicles, once you can drive 250 miles and charge in 5 minutes, you will buy an electric vehicle. If the unsubsidized cost is comparable to an automobile, because the operating costs are far less, the maintenance is almost zippo, virtually nothing, and so it just becomes cheaper. So it's cleaner and cheaper. But the biggest impediment is the degree of misinformation, especially as the technologies get competitive. They're getting a little bit more desperate, and so the volume of the misinformation has gone up in the last several years. Solar was not competitive 4 years ago, the way it is today. It's just totally new world.